This isn't really a mathematical one, but it does make you think about reflections and phases. So there's that picture of a soap film, and it's black on the top. And the question is, how does the very thin part of the film, meaning the black part, cancel reflections at all visible wavelengths? So one thing to make clear is there is a film on that entire circle shown in the image. It's not that it's popping or there's missing some of the film. There is soap there. It's just suddenly, rather than all the colors, it goes completely dark. So how can it go dark? Because we found in other problems that the color you see depends on wavelength, and the wavelength depends on the thickness. So why is it that when it's super thin, why doesn't it look kind of white? You know, when you shine light off of glass and there's no interference happening because it's too thick, you see 4% reflection and things look kind of white. You can kind of see yourself as a ghostly image. So what's going on when it gets really thin? Well, to see that, maybe it'll help if we draw out a really thick section down here. And when we look at a really thick section, you know, we have the standard thing that we always say, like that. We're looking at the reflection between the ray reflected off the front and the ray reflected off the back. And we get an interference condition that depends on the wavelength, and that's why you see the colors. And let's write it down real quick, just because it's instructive and fun. It's 2 times the thickness over the wavelength, the lambda naught wavelength, times the index of the soap, times 2 pi. And then let's do our reflection differences. Why not? Let's see. This is N equals 1. N of soap is about the same as water, 1.3, and then back to air. So in this case, you have a pi phase shift here, right? It was in 1, 1, 1, still in 1, but it bounced off 1.3. And then the transmitted ray, nothing happens on transmission. And here it actually bounces, it's in 1.3 the whole time, but it bounces off of 1. So it's actually 0 phase shift there. And as it comes out, there's no phase shift on reflection, 0 there. So we actually have a phase difference in this one. So let's see, it is 2 minus 1, so it's plus 0 minus pi equals, and then if you want it to be constructive, you would say 2 pi m, where m is all integers. And you'd go solve that. And this shows why soap bubbles are colorful. As they start to get thin and thick, as T changes, the constructively interfering wavelength changes. Okay, because if this is all equal to constants, the only thing you can vary is T, and the only other thing left you can vary is the wavelength that you're going to see. Because N is constant and the reflection order would be constant. Okay, that's just a reminder of why soap bubbles are pretty colors. Why does it go to 0 for all wavelengths? What's going on? Where did this term go? What happened? So what happens is, let's look at it for something really thin. You'd say 2Tn over lambda naught times 2 pi plus 0 minus pi is 2 pi m. So you might say, well, if it goes really thin, that basically means T is essentially 0. And that's right. You could just say, oh, this term's 0. Basically what it's saying is that it's very thin compared to lambda naught. So this is essentially 0 over lambda naught. Then the whole thing is 0. You get no phase shift due to the distance. Right? The distance the light travels in here is basically nothing compared to a wavelength. Well, that's the case, then there should be no interference effects at all, right? I mean, why would we get it at all? But this still happens. Even though the path difference is almost nothing, one is still bouncing off the front with a pi phase shift, one is still bouncing off the back with no pi phase shift. You still get 0 minus pi equals 2 pi m, and you get negative pi equals 2 pi m, and then it just tells you what order you're seeing. Basically is pi, and m is minus 1/2. All right, which doesn't really make any sense. Don't worry about that. The point, the physical explanation is that these two things bounce off out of phase. Thickness has nothing to do with it. Just because of the phase reflections, they bounce out of phase and they cancel. And that's why all the light goes through and it looks black because nothing comes back.